Okay. Thank you all for joining. My name's Tim. I'm here on the user services team, and welcome to my Lunch and Learn. Today we are going to talk about advanced function writing in R, which is a little bit of a loaded title here because it can mean a lot of different things. So our learning objectives today are, we are going to discuss programming in the functional style versus its alternatives, and whatever that means. We're going to write functions for reusable tidyverse style data pipelines with something called tidyeval. And then we're going to parallelize our custom functions with Sparklyr with a little bit of an asterisk on that, and I'll talk about that when I get to it. And maybe a secret fourth objective here is we're going to see some parts of the R programming language that you might not know about. And I think if you're an R programmer, that is probably going to be a little bit fun for you too. So first, I want to talk about different kinds of programming paradigms. So a programming paradigm is a specific style of programming that you would use in order to solve a problem. You can solve the same problems with totally different styles of programming, and many languages specialize in certain paradigms. But in modern times, most modern languages can do pretty much all of it. But I still want to talk about it because it still matters. So I've got four different kinds of programming here, but two of them are really going to be the ones we want to focus on. So one style of programming is called declarative. A declarative program is one in which you tell the computer what to do, but not how to do it. So the big examples here are things like SQL and SAS. When you write a select statement or a SAS proc, you're saying, here's what I want you to do. You figure out how to do it. So because of this, many domain-specific languages are declarative. SQL, SAS, they're all data languages. Stata, if you've ever used that one. The opposite of this would be imperative programming, where you tell the program how to do something, but you don't need to tell it what you're doing. So this is kind of just like generic programming. Copious amounts of for loops, if statements, functions, things like that. When you first started to learn how to program in Python or R, you probably mostly coded in the imperative style. And it's hard not to, right? I mean, this is just programming language, right? But the two stars of today's show that I really want to focus on and contrast here are object-oriented programming and functional programming. So object-oriented programming, or OOP for short, you solve your problems by creating an object and then manipulating that object until you have your desired output. So to put it more concretely, you make a data frame, that's your object, and then you manipulate that data frame with data frame operations in Spark, group bys, sorting it, creating new columns, and so on until you have your desired result. Maybe it's some summary table. Python is generally considered to be an object-oriented language because that is kind of how they convince you to solve a problem. But of course, Python is multifaceted. You could do whatever you want in Python. Functional programming, on the other hand, you solve your problems by starting out with an object and repeatedly apply functions to it in order to achieve a desired result. So think about starting again with an object like a data frame and then applying these actions to it until you have your results. So similarly, group by, sort, things like that, they're all functions. Now, you probably already know how to create a function and how to use a function, but the true hallmark of functional programming is creative uses of higher order functions. So a higher order function is a function that either takes in a function or returns a function or both. So I mean, that's a little bit complicated to say out loud, but think of functions like map and apply, if you've ever used functions like that. Those are higher order functions because they're taking in a function as an argument. In R, everything is a function, even if it doesn't look like a function. Notably, the pipe operator, the percent greater than percent operator, might look like just a regular operator, but actually that is also a higher order function. So even if you've never heard the term functional programming before, you've been using it to some extent this whole time, if you've been using it, the pipe operator, that is. Now that's a lot of talking. I want to show you an example with actual code that should kind of drive this difference home. This is my favorite example. I'm going to, first I have to do some overhead here. This is not a live notebook. I've run this in advance because some of our cells take a little bit to run, but I'm mounting a S3 workbench here, and then I'm doing some R overhead of importing the tidyverse Sparklyr and creating my Spark context. But that's not relevant for the next couple minutes here. So here's a Python cell, and in this cell, I'm creating a class. If you've never used the class keyword in Python, what this does is it makes a new kind of variable. So this kind of variable is called an adder. It's initialized with a variable x, and then this special function called, or special method called call is going to allow me to create and use this object like a function with parentheses. So I'm making a add3 and an add5 object. And this is called making it kind of like a function factory. So I am creating another object that can be used like a function. So add 3 to 7 is 10, and then add 3 to add 5 of 10 is 18. This is a functional, or sorry, this is an object-oriented way of solving this problem of, well, it's a simple problem, so it's not really that complicated, of adding numbers together, right? And I did that by making an adder class, and then addition is done by making new adders. Okay, that's OOP. In R, the way we would prefer to solve this problem is by creating a function that does this for us. So this is going to be very short code that is also very complicated. So you might not understand it the first time you read it. It takes a good couple minutes of staring at this to really understand what's happening. So I'm creating a new function called adder that takes in x. Okay, on the inside of that function, I'm creating another function called inner, and that is a normal thing to call a function inside of a function as the inner function. That takes in an argument y, and it returns the sum of x and y. And then the adder function returns the inner function. So this function is returning a function, which means that when I call the adder function, the output is also just a function. So then I could do the exact same logic I did above, where I made an add3 and an add5 function. Add 3 to 7 is 10, and I can even pipe them together using our favorite tidyverse pipe operator here. And this is solving a problem in the functional style. I take 10, and then I add 3 onto it, and then I add 5 onto it. As complicated as this is, like returning a function from a function, people who get real deep in the weeds on this have even faster ways of writing this. So this line of code right here takes those first 6 lines of code and makes them one line of code. So this is identical to this adder function up above. It's a little bit weird to look at, but people who love to use functional programming love to write functions like this. That's me. I love to write functions like this. It's confusing, but that is actually a hallmark of functional programming. The code is typically shorter, but a little bit harder to read. Once you get used to it, it's not so bad, but this is definitely harder to read, but you can't argue that it's not shorter, right? One line of code. Okay, so that's just plain old programming. How do we actually solve data problems with this kind of thing? So that brings me to part 2. We're going to write reusable tidyverse pipelines using this idea of functional programming. And I want to tell you something that's going to be a little bit controversial at first, but this is something that my grad advisor told me all the way back when I was in school. He said, if you're writing loops in R, you're probably doing something wrong. I think he was even less gentle than this. I think he just said, you're doing something wrong if you're writing loops in R. And I hated him because he spoke the truth. I didn't want to believe it, but the more I learned about functional programming, the fewer loops I've written in my entire life. I don't think I've really gotten rid of them entirely, but you can do everything you think you can do only with a loop without one. And I want to show you some examples, because writing functional style and eliminating your loops will actually be faster in R than using a for loop. So here's what I'm going to do. I'm going to read in 10 separate files without using a loop. And then we're going to carry out various repetitive analyses on these while keeping our code dry. And that is a big theme of all programming, but is especially true of functional programming. That is, dry code doesn't repeat itself. So dry stands for don't repeat yourself. And finally, we're going to split our data back up and save it out into 10 separate files again without using a loop. So remember, we're doing very repetitive things here, no loops. So the first thing I do is I just create a vector of strings here. So I know the names of the files I'm going to be reading in. They're just called December 1 through 10. And then I'm going to define a function called read file by date. And it's just going to import a date. And The only thing in this function is I'm going to use Spark to read a CSV. It takes in the Spark context, and the path is going to be on that workbench that I mounted. So mount advanced R, it's grocery data, and then the date is the name of the file. Header true, schema true, right? And if you are unaware, this function doesn't have a return in it because in R, the last thing that you say in a function is automatically returned. So the result of reading in the data frame is going to be the thing that is returned from this function. Okay, so this function can read in one file, right? If I put like December 7 in here, it's going to read in the December 7 file. So what I need to do is I need to apply this function to all 10 of my files, December 1 through 10. And I can use an apply statement for that. There's a lot of them to choose from in the R language, but one of my favorites, and probably the one I use the most, is lapply. So lapply, the L stands for list. A lot of the applies in R, the thing in the front tells you what kind of object you're going to get back. So what this is going to do is it's going to apply this function I made to every object in this files vector. So it's going to apply a read file by date to December 1, 2, 3, 4, and so on. And then it's going to return that data frame, but it's going to return 10 of them in a list. If you're not clear on the difference between a vector and a list or an array or whatever in R, the lists in R are more like dictionaries in Python, which is a little bit confusing. They're just a collection object. So proof that this works, the double brackets will grab things out of a list. So grocery data list 1, this is the December 1 file. This is the first 5 rows. So it did indeed work. The next thing to do is I need to take all 10 of these objects and condense them into one data frame so I can actually work with it. In Sparklyr, there is a bind rows function. So tidyverse also has a bind rows function, and the way they differentiate function names in Sparklyr is by putting Spark defined function, SDF, in front. So this is basically just going to take a list of data frames and union them. So it's basically a big union all, just going to stack them on top of each other. So now I have one big grocery data frame, and it is about 53,000 rows and 8 columns. Let's take a look at this. So this is a data frame with a date, a store ID. I think there's like 100 of them in here. A region, it's West, Midwest, Northeast, and I think South. Category, frozen beverages, snacks, and a fourth one I can't remember. And then how much money this company has spent on marketing, the price of the object in question, and how many they sold. I mean, it's fake data. I simulated these numbers, but you could pretend that's what's going on. Okay, so now I've read in 10 separate files and merged them without the use of a single loop. Let's do some data analysis on it. So let's say I need to do a lot of summarization. And now I'm going to write a function called summarize units sold. This function is going to take 2 arguments. So the first one is going to be a data frame. And the second one is ... If you've never used ... in R, this is sometimes called lazy dots. The ... says you can put whatever you want here. You just have to know how to process it later. So I can put any additional arguments in these ... that I want, as long as I have something in the function that processes it like a list. And so what I'm going to use here is a very confusing topic called tidy_eval. So if you've ever used the tidyverse functions and wondered why you didn't need quotation marks when referring to column names, that's because R has this thing called tidy_eval, which says if somebody brings in a variable name that's not a variable, we're just going to assume it's a column in the data frame. It's something that you've probably been using without even thinking about, but the back end of it is actually very complicated. So to use tidy_eval, I need to enclosure this object. So this is going to be the arguments that I put into this function, and I'm going to call it group sims. When you bring in tidy_eval stuff, it's called a symbol because it's not really a variable. And then what this function is going to do is it's going to take this data frame, group by those variables that I put in, and this triple exclamation point kind of splats is actually the term for it, splats them back out into the variable names. So if I put like 3 variables in here, I'm group buying them is what's happening here. And then I'm going to summarize it. I'm going to count how many were in these groups, and then I'm going to take the total number of units sold in these groups. This is hard to read, especially because tidy eval is extremely confusing to read. I have a link here if you'd like to learn more about it. I wanted to find a good blog post that gave a quick tutorial on how to use tidy eval, and I found one that happened to be written by a former colleague of mine. So give his Medium post a click, and he actually has a very well-written blog post here. Okay, so anyway, I've written this function, and I'll show you how it's used. I'm going to take this df grocery data frame, and I'm going to summarize it by date. And then that's it. This is just going to bring it back into memory so we can see it. So this is going to take date in as the lazy dots. So it's going to be data, group by date, and then summarize. And now it's summarized by date. I can also do it by region and category. And here it is. By both region and category, it's grouped by. And I can keep going here. The point is that I can make all of these summary tables with this one reusable function over and over and over again. So I've actually written a complicated function here that I can pipe into it in a tidyverse and Sparklyr safe way that does a lot of data analysis for me without writing redundant code, right? We're keeping our code very dry here. Okay, so this is what I'm calling data analysis for now. Let's write our results back out without using a loop. So here I'm going to grab all of the unique store IDs. I think they're just random numbers between 100 and 200. So there's like 100 of them here. And now I'm going to write a new function here called write by ID. So we read them in based on date. There were 10 files, December 1 through 10. And I'm going to write them back out, one file per store ID. I think I misspoke above when I said we're going to write them back out as 10 files. We're actually writing them back out as 100 files because there are 100 store IDs. So inside this function that takes a store ID in the data frame, I'm going to take the data frame, filter it down to the store ID in question, and then write it back out to grocery output store underscore 148 or something like that. And I'm going to overwrite it. And then I have some cat statements up here. If you've never used cat, it's basically the same as print, but you don't have those like annoying block numbers next to it, like this. So it's going to say writing ID and then done. And of course, I've already pre-written this notebook so you can see below what the output here looks like. But here again is another use of the lapply function. So I just did the first 5 here. I'm going to take all these store IDs, apply them one at a time to this write by ID function that I made. And then I'm going to set the data frame to be the grocery data frame that we've been using up until now. And what this will do is it'll take all the store IDs, write them out by ID. Without using a loop. Again, common theme here. Okay, finally, some more astute R users might notice that this is also a little bit inefficient because Sparklyr already has a shortcut for this. So if you want, you could just do this. You could just use Spark write CSV with a partition by based on what you want. Now, that doesn't handle every case because what if you want to do a special kind of write that's not just by one variable or one group of variables and you want to do some additional processing to it? There's more to it than just a partition by. But if you wanted to do exactly what I've done up above, partition by is probably your better bet here. Okay. Cool. So we've learned how to use apply statements and tidy eval to write functions that basically make the writing of our code really efficient, right? We've done a lot of complicated stuff without loops, which are slow in R, in the functional style, which means that our code actually ended up being a lot shorter than it would have been otherwise. Now what? I want to show you how to do something that has been often requested of us in the help desk and things like that, because not everything is Spark safe. Right? Not everything that we want to do to our data frames has a distributed function for it in Spark. So what do you do when you have something you want to do, but you can't do it in Spark, but you need to do it in Spark? And if you were using Python, you'd probably reach for a UDF, a user-defined function. Sparklyr does not have UDFs. What it has instead is the Spark apply function, which will take a function and fill the same role that a UDF does. It'll apply it in a specific Spark safe way. I do unfortunately have some bad news. is that Spark Apply does not work in Databricks at all in any runtime version. This is a big holdup to I think would be meaningful distributed R work at scale, and I hope it's fixed soon or implemented soon. So take everything I'm about to tell you with a big grain of salt on that. Unfortunately, we can't quite do it. I'm going to give you an alternative at the end here, but this is, big frowny face here. It's really annoying because this would be super useful for, I think, a lot of our users. But also, I do want to say that even if it was possible, you basically never need this. When I'm working on the help desk, a user will often come in and say, help, I need to create a UDF, or I'm trying to use Spark Apply because I want to do this. And 99% of the time, there just is already a Spark function for them, right? There's a more creative way sometimes to reach for that is Spark safe and fast and distributed. Spark Apply tends to be really slow because you need to broadcast non-Spark things onto your cluster, and that's usually a huge bottleneck in your code. So I also want to say that you really probably don't even need Spark Apply, even if you really wanted it. That being said, there's one example where I think a lot of our users would really have liked this to work, and that is when fitting machine learning models that are not parallelizable. The big example here are mixed effects models using the LME4 package. So the LME4 package, which has mixed effects models, if you've ever dug into the background of how these models are fit, they're fit, I think, using some form of gradient descent, which is famously not parallelizable. So there will never be a mixed effects model that works with distributed calculation. Logically, that's just not how it works. Same thing with a lot of like Bayesian tools and stuff like that. These are sequential algorithms. They cannot be parallelized. So what you might want to do is you might want to group your data frame and then apply a mixed effects model to each of these groups in turn. This is when you would use Spark Apply, and I'll show you how to do that. So what I would do is I would create a function called add predicted values. And in this case, I'm just going to do an OLS model here of just a regular old linear regression. And here I would make the model, and I would append the predicted values back onto the data frame, and I would return the data frame. The Spark Apply function takes in a data frame and returns a data frame. So then what I would do, and I'll uncomment this, but I need to comment it again because it's not going to work. You would take your data frame, group by whatever group you wanted to do it by, and then Spark Apply that function. And what this would do is it would take in that data frame, fit your model, append the fitted values, and spit it back out. So I apologize. This would be super cool if it worked, but unfortunately, it does not work in Databricks. If you ever find yourself in a situation where you are running Spark, not in Databricks, you could do this, but I love Databricks, except for this part. But yeah. Okay, so an alternative to this would be a much slower way to do it, but I want to show you that anyway. So what I would do is I would, do it in this slow way. And this slow way will only work in two specific cases. Both these conditions have to be met in order for this to work. The first is the data in each of your subgroups has to be small enough to be pulled into memory. And the number of groups you have isn't too many, because remember, you're splitting this into a parallel calculation. So you're going to be pulling them into memory, and if your data is too big, it's going to be a really expensive operation. So basically, this big data solution only works if your data is not that big, which is unfortunately generally not going to be good enough for, I think, a lot of use cases. But anyway, here's how it would work. I'm going to write another function. I use the same name here. And what I'm going to do is on the inside of this function, I am going to filter it down to the group. In this case, it's region. Filter it down to the group in question. And then I'm going to call as data frame. This is a very innocuous looking function, but this is what makes this so slow. The as data frame function pulls your data frame into memory, where formerly it was a Spark data frame that was lazily evaluated and didn't exist in memory. Now I'm pulling it into the memory of the driver node. That is a expensive operation, and if your data is too big, it'll also break. So this is the bottleneck here, this one line of code. Then I do the same thing, where I fit this model, append on the fitted values, and then this line of code will actually cast the data frame back into a Spark data frame, which is an expensive operation, but not as expensive as what happened on line 2 here. And then I return that Spark data frame from the function. And then I just run an lapply, and I union all again. That's what SDF bind rows did. And again, this is not a live notebook, but there is proof here that this does work, where I display it. And if you look all the way on the right here, the expected sold, which is our fitted values, did indeed get successfully appended here. So this would work if you were using it. Only if your data frame was small enough, unfortunately, is not always the case. All right, let's conclude here. The designers of R want you to code like this. They want you to code in the functional style. It's built into the underpinnings of the language, right? Loops are slow in R. Functions are fast. So they want you to code in this functional style, not just the procedural one. And there's lots to be gained by writing shorter, smarter code. It is more reusable and modularizable, right? I like to show the example of if your function breaks, you don't have to fix it 10 times, you only have to fix it one time. Modular code is much easier to maintain. Building your own tidyverse style functions can make your code shorter and clearer, especially when taking advantage of the apply style higher order functions. So if you're going to be doing something many times, it probably should be in a function. In R, they actually want you to just write everything in a function. So if you're going to do something more than 0 times, put it in a function, but not everybody goes that far. And then finally, Sparklyr has this Spark apply function, which can brute force operations that aren't built into Sparklyr. But as I mentioned earlier, it just is incompatible with Databricks, which is a huge bummer. Also, even if it did work, this function is very error prone, and it currently can't fit models, which would be its chief utility. But I mean, again, it doesn't even work in Databricks at all. And the big bullet point here, which is maybe the most important, is you pretty much never need this. And even if you did think you needed it, you should avoid it at all costs because it would be so slow. So again, it doesn't work. That sucks, but you almost never need it anyway. So it's okay. Okay, I'm done here. Thank you so much for listening. I hope this was a cool insight into some aspects of the R language that you might not have used or even seen before. And I realize I've got 1 minute left and you have a survey. So thank you again for joining, and I'll